All right. So, good to see you all here. In the way of announcements, I have some not great announcements. But, I'm going to go ahead and level with you the current situation. So, we were reserving for like rooms next year. Due to some circumstances, someone was able to get this room right here before we did.
Due to the room reservation system just being genuinely terrible.
Due to room reservation and stock and everything about that just being.
Because you tried literally like within the first minute. And
oh
it was
yeah, I started the reservation at like 5 seconds in. So by the time I figured out that it didn't let us get this room, it was by now 10 minutes because I had to enter in all my information again. This system's terrible. I later booked a bunch of rooms in the SSA, but I wasn't able to like get anything consistent. Basically, we're down to 2 options and 1 long shot option that I'm gonna check tonight, but it's probably not gonna happen. But really the 2 options come down to either we room hop and each week we just have one of probably, it's going to be about 4 different potential rooms we could be in, which isn't great, but 3 of them would be here in the SSA up on the 4th floor. So they'd be mostly in the same place most of the time. So we have that option, or to move the meeting to an 8 to 9:30 slot, which would make our dinners have to be beforehand, which has a whole host of issues of like transporting people, and the dinners have also served as kind of nice people talking about
fellowship.
Yeah, stuff of the meeting and everything, and kind of carrying on those conversations, which we would totally lack. So that's kind of the situation. I just wanted to share with y'all. If y'all have any like, you know, adamant, like, I think we should do it this way or something like that, like, please let us know. There'll probably be like something in the Discord to just be able to kind of voice your concerns with that. But we're trying to work out a way to get it. There's also a small potential that maybe we can move it to a different day, but I'm doubting that that's going to be able to work, because at this point it's so late in the reservation, I don't think we're going to be able to get any day consistently. So we might as well leave it on Thursday if there's not going to be any other consistent day.
The rest of this semester is fine. Like I thought that was
Yes.
all reserved like ages ago.
This will only start taking effect as of January. Yeah.
So obviously we'll let you know in the Discord if we have any updates about this. We'll come to some sort of decision about what we're going to do, and we'll let you all know. And we're thinking about maybe asking people for input. We're kind of leaning towards the room hopping right now.
Yeah, honestly, we're leaning towards room
Since
hopping.
that's the earlier meeting time and it's easier to coordinate dinner.
Just to really kind of keep the dinner stuff going, and also same meeting time. And also 8 to 9 for like the official meeting is pretty late. Like, so, but if anyone has some like real big opinions on this, like, please just, you know, let us know after the meeting tonight or whenever on the Discord. But this will be something that we probably will have to make a decision on pretty quick, because SOC is currently like putting on ice until we make a decision. So anyway.
Hence the announcement, like the time pressure.
Hence the announcement.
Yeah.
Also, just to give y'all a heads up, like a quite far out heads up, that next semester in any case, things are going to be working differently. So just
Find the algebra, the permutation groups of the
So yeah. And more happy news. Thanksgiving, as a reminder, is on Friday the 17th. So that's a week from tomorrow.
For those of us who don't know yet, Thanksgiving is effectively a potluck Thanksgiving kind of deal.
Mm-hmm.
And if you want, we have a little challenge going back to the founding mythology, so to speak, of whatever your dish is, it can't cost more than $20. This is an optional challenge, but it really brings back the spirit of cheapness that unites us.
Exactly.
Hence the name.
It's supposed to be just kind of a nice, easy, cheap potluck. Nothing fancy. Yes.
Speaking of dishes, is there going to be a place to sign up for who's supposed to be?
Yeah,
Uh,
that,
Oh, all right.
what do you think?
I was thinking we just do it at random and let luck decide if we have a main course or not.
Everyone just brings.
I kind of like
I feel like
Caitlin's
maybe both.
suggestion on that.
Kind of have like things for like main stuff, like main protein and some couple of main sides, and then other than like maybe 4 core things, everything else can just be like whatever people feel like.
If we wind up with nothing but turkey, that's perfectly fine too.
Yeah.
Are we allowed to bring duck foods?
No.
No, that's the one rule. Nothing with duck in it. As president, I'm making that rule.
I object.
No.
So no turducken then? Okay.
No turducken.
Darn it.
That's a day for the law.
But duck tastes good.
Anyway, but yeah, I think that'll probably be good. We just kind of have a list of some, like, the main stuff that like needs to be there for a Thanksgiving meal. Other than that, bring whatever, and we will make something do. And again, cheap, nothing fancy. All right.
No ducks.
No ducks.
Correct.
I will leave it over to.
Before we start though, can I mention just real quick about, Tim
Or I'll leave
McGrew
it
is
there.
coming next week here.
Tim McGrew, yes.
And it's gonna be a really nice special event. He's a philosopher with PhD. He's also a really prominent Christian apologist coming here from Michigan. And so we're actually doing that as a joint thing with the Atheist Christian Book Club. So it'll be a real interesting environment here of discussion. There'll be about maybe 5 or 10, maybe probably 10 people coming from off campus or so and entering into the discussion. The topic will be on defending the Bible, the New Testament in particular, showing its historical reliability and whatnot. So I think you'll find it really interesting, and hope you can come bring your friends. And we are really glad to have Dr. Whalen here. He's our faculty sponsor. He has a couple kids. He's kind of busy, so he used to be able to come here a bit more, but we understand. We're just glad to be able to have him come and talk on this interesting topic. So I don't want to eat up your time, so take it away, Tristan.
All right. I don't think I need to give like a commercial or advertisement for mathematics to this group. I think most of you appreciate that science comes up so much here, logic and reason, and mathematics is like the foundation or the big boss of all of that, right? So like, you can't do science without math, you can't do chemistry without math, technology, engineering, all rely on mathematics. So I think everyone appreciates the importance. I also want to make sure that when you hear the word mathematics, I mean, in your day-to-day life, you might think of like figuring the tip at a restaurant or adding numbers, number crunching, but any math major can tell you that some days the only numbers in my notes were the date, and everything else, well, just try it out sometime. And I brought some books. There's a lot of cool things in math, interesting shapes, surfaces, worlds, whole worlds lurking in mathematics beyond just rote arithmetic that you might not be aware of unless you're a math major or an applied math major. Just for kicks and giggles, I included a few screenshots from my thesis from nearly 8 years ago now on Friday the 13th, March 2015. I still distinctly remember typesetting all of this. And I'm not showing this to like impress anybody or anything. Just let's all just bask in the amazingness of like, wow, that means something to somebody. One of my big contributions was typing out the proof of this theorem about short exact sequences of the k-algebras of certain types of algebraic groups.
There are still
Hardly a
numbers
number
in here.
there. What?
There are still numbers in here.
That's true. I know. There are still numbers, but they're just serving the purpose of indices, right?
Yeah, those don't count.
Also, are these vectors of numbers or vectors
You
of
wish
some
they
other-
were that simple.
Or like-
Think of like generalizing vectors to more than just number fields, and then generalizing that to more than just dimensional vectors, and generalize that a couple more times.
That hurts my head.
It's been a while. It's been a few years.
Oh, man.
But there's a deep world here. Just flip through a few books after the talk, and if to cure you of the idea that math is
So
just number
basically-
crunching.
So basically group theory applies to a bunch of stuff that are.
There was a little bit of group theory somewhere in there. and functional analysis. I was trying to think, how would I summarize my talk in one sentence? Like you need a thesis, right? That one sentence. And I couldn't come up with it. Instead, I came up with this slide. And I think it says the whole story. You've got mathematics, proofs, theorems, logic, science, technology, engineering is built out of it. And then you've got religion, all those fun stories people tell, and there's lots of religions, right? And who knows which one is right. Religion's like with arts and culture, and really that's more of an opinion. I think these two different worlds, I thought, was a feeling I had as a student. Math is the world of proof. Religion is, well, not that. There seemed like this dividing line between the two. It seemed like these are worlds apart. Two different kinds of thinking, two different things. And the thesis of my talk is to show that, no, there's not a line between them. There's a whole lot of religious-like things in math, you just don't use the same words. And there's a whole lot of ways that math can help with religion, especially the most complicated, paradox-ridden religion of all, Christianity. So that's the thesis of the talk, is that there is not a line between them. They merge and blend, especially with Christianity. As a math major, I felt like it was my duty to kind of be a math guy, right? And so one of my first investments was the 4-volume set, The World of Mathematics. Collected articles and things. What better way to go to sleep at night than some just leisurely reading? What could be more innocuous than an essay from this book? And so I'm actually dutifully chugging along in my carefree college days. And then I get to an essay by a guy called Bertrand Russell called My Mental Development, which is kind of like a story about how he grew up and his philosophy, his worldview. Why should I care about Bertrand Russell's worldview? Well, we'll get to that. But I got to this paragraph from World of Mathematics. For 3 years, he explains, growing up, I thought about religion with a determination not to let my thoughts be influenced by my desires. I discarded first free will, then immortality. I believed in God until I was just 18, when I found in Mill's autobiography the sentence, my father taught me that the question, who made me, cannot be answered, since it immediately suggests the further question, well, who made God? In that moment, I decided that the first cause argument is fallacious. So we see this kind of almost mathematical feeling, logical claim. Well, if I ask myself, who made me? Who made all this? When the answer is, well, God, of course, the first cause and all. Well, then the follow-up question is, well, okay, well, who made God? And then who made that? And then who made that? And so he rejected the first cause argument, or at least decided it was fallacious at that moment. So, for the first time, these worlds started to, religion and mathematics, and unsuspecting me, suddenly faced with this little argument, and it got me for a little bit. So our first lesson, our first Christian lesson from mathematics, is how to respond to this. And so I asked the audience, what's your response to, well, who made God?
That question is only important for things that began to exist.
Oh, okay.
Good
Yeah,
answer.
there we go. Uh-huh.
That question is only important for things whose existence is contingent.
Oh, man, getting even
Also
more
good.
vocabulary.
I
And
love
starting
it.
with
Which
the
can be-
easy thing and
which can
building
be-
up to the harder lessons.
Which can be which is something which I argue can be predicated of things that have existed infinitely in the past.
You're even making my head hurt.
And therefore did not exist.
See? Math and Christianity just works. The response is, for me, my response as a math major is about that which begins to exist would have a cause. The question is, well, is God a thing that begins to exist? And we go into the idea of, well, what do you mean by God? What is the definition of God? Now, this is not to say God exists. In mathematics, you define things all the time without asserting they exist or not. But the question, who made God, is simply not a logically valid question, because if anything is true about what is the definition of God, it is well, God is something that is not created. God is something that what y'all said did not begin to exist, just by definition. Whether God exists or not, whether that defined thing exists, well, that's up for discussion still. But being silly about the definition and ignoring the fact that no, God implies something that has always existed, contingent, didn't begin to exist and all that. And all through being a math major, definitions was such a key thing, right? You constantly had to invoke what a word meant. What does this term mean? And here I was applying it to religion. My math classes and that rigor of the precision of definitions was suddenly helping me out with sudden, unexpected religious arguments appearing as I wandered around in the math world. There's the first lesson. The next lesson has to do with one reason Bertrand Russell's famous with respect to mathematics, anyway. The next lesson has to do with axioms. And this is the fact that you cannot prove everything. You can't prove anything without making an assumption. You can't prove anything without making an assumption, which was actually not obvious to me in my early days as a math major. As a math major, I think math is the world of theorems that have been proved. You go to Wikipedia, look up a list of theorems. Here's a snapshot of the first couple dozens and dozens of famous theorems, and that's just the tip of an iceberg. And if you take your pick of a theorem, and if someone says, oh, I disagree with that, I don't believe it, oh, there's a proof. You can't disagree with it. It's been proven, right? Skim down the list. Central limit theorem is around here somewhere. I teach that in statistics. Central limit theorem's there. Several other fun ones in that list.
You didn't prove it in your class, though.
No. That's no. I didn't. Oh yeah, you're in there. I gave evidence that it was true, though.
At least he was awake.
Well, there you go. Nice. But you take a pick a theorem, and if you disagree with it, well, there's a proof. There's no argument. Skim on down the list. This is the last slide with snapshot. There's dozens. Here's fundamental theorem of calculus. Someone comes along and says, I don't believe the fundamental theorem of calculus. I don't believe it. Well, here's a proof. Sorry, you can't disagree with it. You can't object. But every mathematical proof is built on a foundation of axioms, things that are just assumed, things that are just accepted as self-evident truths, stated without proof. Mainstream math is kind of up here. By mainstream math, I mean what we see in our classes. Theorems, only math majors start to see them. Those are built on a foundation of set theory, and that is built on a foundation of just unproven, asserted axioms. And it was a major threshold for me in my learning. Oh, wow. Even in math, you've got to just accept some things on faith, even in math. And for a while, for centuries, it is now called naive set theory. It was just accepted that we know what we mean when we say a set of things, of elements, the set of odd numbers, the set of rational numbers, the set of squares, the set of circles, things like that. But Bertrand Russell came along, and one of his things was coming up with a brutal contradiction with naive set theory. And it leads to this contradictory scenario. Bertrand Russell said, well, you just take for granted you know what you mean when you define a set of these things that meets these requirements, like a club, and you're in the club if you meet these requirements. Well, what if I say, let A be the set of all sets that are not themselves elements of that set? Does the set A, in fact, contain itself? Just say, I want the set of all sets that don't actually contain themselves as an element. Does that set contain itself? And then you reach a contradiction. Well, if it does contain itself, then it should not belong to itself. And if it does not contain itself, then it should belong to itself. If set theory isn't your thing, consider this. Everything I say is a lie, I am lying. It's like that logical loop. We're like, well, wait a minute. It just is a nonsensical. So that wasn't acceptable. That wasn't acceptable. And in the early 1900s, some mathematicians worked to put some rigor on the axioms of set theory. And two of the main names associated with that are Zermelo and Frankel. And so instead of just naively assuming we know what we mean, a clear foundational structure was given for all of mathematics. I mentioned there are other systems of axioms to choose from because you can't prove them. Therefore, well, if I don't want to accept it, here's Zermelo and Frankel. You know, any math majors might like, oh, okay, there they are, Zermelo and Frankel. And here's their menu of axioms. The mathematical creed. If mathematicians met every first day of the week and recited a creed, they recite this. It's stated in plain layman's terms, right? These aren't really what they say. So it's the mathematicians, the analogy is describing like God as like up in heaven. I'm limited by my use of words. Same thing happens here. To try and explain it without getting into the technicalities, I'm limited by my use of words, like members and this and that and all. It looks messier than that. Question? You don't believe it? You don't have to. They're axioms.
I typically hear of a ninth axiom included.
That's
He's going to get to
coming
that.
up. That's coming up.
Okay.
No spoilers.
Okay. One.
I left some empty space there.
Yes.
And I mention again, these are not theorems. These are not proven. These are just accepted. Or you're not doing mainstream math. There's no logical compulsion to accept these. And there are other axiom systems. Zermelo-Frankel's the one that's the most common. There's also one that's built all out of the natural numbers. There's a famous quote in mathematics, God made the natural numbers and everything else we came up with. And throughout mathematics, there's this idea that you can start with the natural numbers, 1, 2, 3, 4, 5, 6, 7, and so on. Most people don't include 0 as a natural number. But this mathematician, a different kind of axiom theory, something with types and not just sets. Von Neumann and a couple others, a different kind of set theory. Another kind of set theory, Morse and Kelly. It's like, well, there's so many different denominations of math. Can I trust what I learned in calculus? Can I trust as 2 + 2 = 4? They need a mere mathematics, right? Like C.S. Lewis wrote Mere Christianity, and every denomination accepts it. Many of our math books in the math classes are mere mathematics. Just the common ground, like any mathematician would accept these. And just the parallel analogies just were so amazing to me. And how do you decide, right? How would you decide whether to just accept a set of axioms or not? Why are the Zermelo-Frankel axioms like just accepted? Why are mathematicians okay with accepting them? Well, here's how. From the greatest advanced math book ever written, Topology book by Munkres. Here's how. Do they provide a foundation broad enough and strong enough that the rest of mathematics can be built on them? What are you able to prove with these assumptions? Do they make sense? You could say, as an axiom, there isn't any set. And that, you could just say that. Math is all just a sham. You could say that, and you can't would you prove it right or wrong? But you can't do anything with that. What explanation is that? No. Is there a foundation? Do they lay a foundation where you can do a lot with them and yeah, that's right. The Bible has a phrase for this quote. Judge a tree by its fruits. Judge the axiom sets by the theorems you can prove. Judge a tree by its fruits. So for example, this is the one that prevents Russell's paradox. You can't just define any old general entity. You're restricted to defining subsets by a logical operation in terms of these axioms. I use words instead of logical things. Another one of them, Frankel added this one, Because there were some sets that all mathematicians, all set theorists said, just took for granted that certain sets existed, having to do with a set of natural numbers, and then the set of all sets of natural numbers, and the set of all sets of natural numbers, and set theorists just took for granted that was a thing. But without that axiom, you can't prove that exists. So think of that. Backtracking. Backtracking. Because we couldn't prove that something existed that all mathematicians agree, no, that exists. Okay, well, let's establish an axiom. Let's lay that brick in the foundation so that it does. Think of that. Backwards working. This one was to courtesy von Neumann for his theory of ordinals like rankings and cardinality. Again, that idea of backwards logic. Wait, let's go back. We need to say that, else stuff we know is true can't be proven without that axiom. It's like the development of the church creed, of the Christian creed. Like, oh, we need to say this. I'll get to some examples in a bit. You know they're right. You just know they're right because of what you can do with them, because everything clicks, because the things you just know that mathematicians just knew had to work can be built from it. In the words of Christian writer Chesterton, if a key fits a lock, you know it's the right key. If the axiom lets you prove things that you just know are right, you know it's the right thing. You just know it's the right thing. They're the keys that fit the lock. The set of axioms are the keys that fit the lock. Diagram of a key. Take a break from all the words on slides. When a key fits a lock, you know it's the right key. When the axioms, all of math flourishes, you know it's the right axiom set. When the doctrine, whatever crazy paradoxes are in it, when everything else makes sense, you know it's the right doctrine. So there is a ninth axiom that used to be controversial. There is a ninth axiom that now the phrase is historically controversial. That's what mathematicians say now. The axiom of choice. If you have some collection of sets that have stuff in them, then you're able to arbitrarily pick one element from each of the set in that collection. Like if you have a line of jars full of marbles, you can form a new set consisting of one element picked from each set in your collection. If there's finitely many sets, then there's no issue. There's no controversy. The issue is, well, arbitrarily many sets, infinitely many, like one for each counting number, and then making an arbitrary choice from each set. The issue with the axiom of choice, like why was it controversial for a while, is like, wait, are we really able to make arbitrarily many arbitrary choices? Is that really allowed? Like, we can do finitely many, like roll a die or reach in and draw it random finitely many times. But surely it's a contradiction to say for infinitely many. And it first showed up in a theorem proved by Zermelo, the well-ordering principle. It says for any set A, you can put it in an order so that whenever you take a subset of it, there is a smallest element. Now, the natural numbers have a smallest element, 1. The number line, or the integers, there is no smallest element. And so a mathematical instinct, the reaction to that is to think, that's crazy. Sure, the natural numbers start at 1, and so there's a smallest thing, but the real numbers just go on forever to the left, negative. And like you could come up like any set like that, you can put it in an order so that any subchunk has a smallest value when things like the real numbers just go on forever smaller and smaller, integers. And in Zermelo's proof showed up the first time the axiom of choice was used. This idea of making arbitrarily many choices from arbitrarily many sets. And so mathematicians reacted to that like, wait, there's no way that's true, is the reaction from a mathematician. That can't be right. And here's where it looks like there's a problem with your logic. You've made arbitrarily many arbitrary choices. But getting used to it, like, okay, maybe it's not that bad. So the joke through grad school as a mathematician was that the axiom of choice, well, that's obviously true, and the well-ordering principle is obviously false. Like, there's one thing that's clearly, that's fine, that's intuitive, we can choose a bunch of things, and then smallest element? Well, that's ridiculous. Think of like the real numbers or the complex plane and things. But unfortunately, they're actually logically equivalent. The mathematics behind the scenes says that if you assume this, you can prove that, and if you assume that, then you can prove this. So it's like, can you, like, what's the phrase, like, in you're inviting trouble, like, you want this, because that looks like it would work well, but then have to eat that. Don't ask me for the proof. It's in here.
But I do have a question.
Go
about that
ahead.
principle. So, this order relation,
Yeah.
I would imagine it's not the normal order relation.
An example of one is like
like-
less than. Yeah. But there are
It's
other
not-
order relations.
So you could take okay. Well,
Yeah, like if you had a
discuss.
pair of numbers, you could do like a so-called alphabet order relation, like cycle through the first one and then cycle through the second one, for example.
I mean, you could take f of x and then say that the order relation applies to f of x instead. Okay, no, let's not get into that.
There's
Right.
probably infinitely many
Right,
order
This is
relations.
not a math class.
I included the descriptions. What I wanted to show was standing precariously in tension in math as these two statements, these two doctrines. And once you accept one, you're stuck accepting the other. And over time, mathematicians have decided pretty much to accept the axiom of choice and swallow the well-ordering principle with all its nonsense along with it. And I see a similar thing happening with many Christian doctrines as well. For example, if one essential axiom of Christianity is that Jesus is 100% God and 100% man. Another one, we have an all-powerful God, and yet at least at some point there was human free will, at least at the fall. There's debate among Christians whether we still have free will or if it's just all rotted by the fall, but at least at some point there was free will, and yet there's an all-powerful God. Scripture is both authored by God and authored by men. And had to state a doctrine with the little math symbols there. The idea that our meriting salvation isn't even a smidgen due to us. Isn't even a smidgen. It's 100% God.
I kind of want to get a shirt that says heretical for every epsilon.
Needs to be written. Hey, our next T-shirt.
Heretical for every
You're thinking like an entrepreneur.
Heretical for every episode.
Having been dragged through the brutality of math and those axioms and proofs, these are almost like, oh, that's easy, that's obvious, compared to the axiom of choice and the well-ordering principle, compared to some of the other paradoxes we'll see in mathematics. Mathematics almost like prepares you to encounter the things Christianity says. Like, oh, okay, but that happens in math too. It's almost like obvious. And for a set of axioms, like here's the Nicene Creed, it's not that different from what mathematicians do. Here are the axioms, and from these follow truths and theorems, if you will, explanations, facts, strategies for living. So it's not Zermelo Fraenkel, it's the Nicene Creed, and some few hundred church leaders decided on them, but that's not like some, oh, those Christians coming up with after the fact their truths. That's what mathematicians do too. Working backwards at, well, it must be that Jesus was fully man and God. Just like in mathematicians, well, it must be we need that axiom there to avoid Russell's paradox. Like that's what makes everything work out. There's the second lesson about axioms. Once you get used to axioms in mathematics and including some of those tense ones, like, Christianity suddenly doesn't seem so different than mathematics in a way. Like, it's not like its own little fluffy thing. It's the same system logic. This third lesson now, moving on from axioms, The third lesson is the difference between proofs and evidence. Proof versus evidence was a crucial distinction for me. You've got to hand it to Christians. Like, if Christianity isn't true, we sure are making ourselves vulnerable with saying, you know what, approximately the year 30, under this Roman governor in this location around Jerusalem, there was a guy walking and talking. Like, if we had lived and we could walk up to him. And this happened, and then he rose from the dead and was seen by people. Not in some vague, hazy, just some arbitrarily distant time passed, in some arbitrary plane of cyberspace or reality or anything. No, at a definite time and place. Like, if we're all making it up, we sure are sticking ourselves out to be very vulnerable with these things where you can test them with evidence. You can at least see, well, wait a minute. Okay, that's either true or false, that's either true or false, but this, you're saying something actually happened, specific year, specific time, specific place. And I would not only say those are axioms, but are also like evidences, or things you can at least analyze the evidence for, as is done here. So the third lesson is distinguishing, using carefully the words proof and evidence. And I love including this quote in my probability and statistics class. And normal law of errors is basically the central limit theorem. Everybody believes it. Well, the scientists, the experimenters, they think the mathematicians have proved it. And the mathematicians think it's true because they think the scientists have observed it. Proof and evidence there. Oh, the mathematicians, they had to have proved it. And oh, the scientists, they have to have seen evidence of it. But great quote there from a physicist and a mathematician there. I think the next paragraph I'm about to show and read from illustrates the principle, illustrates the idea I want to convey with this lesson better than anything else. And it comes from the autobiography of the Christian writer G.K. Chesterton. I think it just speaks for itself. His autobiography opens with this paragraph. Bowing down in blind credulity, as is my custom, before mere authority and the tradition of the elders, superstitiously swallowing a story I could not test at the time by experiment or private judgment, I am firmly of the opinion that I was born on this date in this place. My birth is an incident which I accept like some poor ignorant peasant, only because it has been handed down by oral tradition. I love that paragraph. It just speaks for itself. Prove you were born. Well, I mean, presumably I was there. Other people get born. Surely I was too, but would it be any logical contradiction if I wasn't? I have evidence, but I couldn't prove it. Prove that you're not dreaming right now. Prove that you're awake right now. Prove that you exist right now. Well, proof versus evidence. Like, okay, hold on. It's back to that whole axiom thing. We're not going to prove everything. And in mathematics, it starts with evidence and builds to proof anyway. It's like this paraphrase of a quote from the famous mathematician Riemann. If you take calculus, you know Riemann's name. Tell me what's true and I'll prove it. But, well, what is true? That's the tricky thing. If you tell me it's true, I'll furnish a proof. The hard thing is figuring out what's true. And how do you figure out what's true? Looking at evidence. You start with looking at the evidence, walking around and, well, is there evidence that this thing is true?
Well, if he couldn't furnish a proof for his hypothesis, maybe it isn't true.
Well, that's the thing. Here. The Riemann hypothesis. How important are proofs to mathematics? That's one of the things that made me have my wall between math and religion. Well, there's two different thoughts represented by these two mathematicians' quotes. At one extreme, and the other extreme. At one extreme, logical proof is like the decisive, distinguishing feature of math. At the other extreme, well, the rigor is just to justify conquest of intuition. It's interesting that even in math, there's not this agreement like, oh, everything is proof. I won't mention like this was a French mathematician, this was a Russian mathematician. That might have something to do with it. But this quote about math kind of reminds me of a famous quote from the scientist that everyone knows and loves, Einstein. The whole of science is nothing more than a refinement of everyday thinking. Perhaps mathematics is just, in a way, a refinement of everyday thinking, and the proofs are there just to give credibility to those intuitions. So tell me, what's the difference between proof and evidence in your own words?
Evidence suggests something may be true, proof is definitive.
Nice, well said. Evidence suggests what is true, whereas proof is almost, you could say, conclusive, like compels you.
Evidence is observed, proof is reasoned.
Okay, yes, I like that. I like those word choices. What in your life, what decisions do you make based on proof, on 100% certainty that it's true?
Not much.
Not much. Anything? Is there anything? Like the existence
Only when I'm
of,
doing math problems.
right,
or something.
the existence of matter, that I can trust my friends, that I exist.
I think I can prove that I exist.
Yeah.
I couldn't prove it to you, but I can prove it to me.
Oh, right. Well, would that be right? So, like, that's the thing, right? I'm just mentioning this is an important
I see a
distinction.
distinct shape.
And-
I'm pretty sure that distinct shape exists.
You're pretty sure, at least.
What if your Boltzmann maps? What if you're a Boltzmann?
Keeping this distinction in mind has helped me a lot in navigating the crazy things in math and the crazy things in Christianity. The crazy things, paradoxes, my favorite, well, and the last thing's my favorite, but this is even more my favorite. Anyone know why I included this mathematician's not only year, but dates of birth and death?
He died on Pi
He
Day.
did, on Pi Day, March 14, 314.
Every mathematician's dream.
In a way, paradoxes.
He died in 2018, not in 2015.
It's true.
Right, Super Pi Day. The year I defended my thesis, the day after I defended my thesis.
Should have scheduled it differently, huh?
In 2015, though, it was 3 years later that he passed away. Christianity has paradoxes. I showed 3 or 4 of them earlier. Mathematics has paradoxes. I have a handful here. Sorry if I leave out your favorite. One of them is this great blend of the infinite and the finite. Curve y equals 1 over x squared from x equals 1 to infinity. That's an unbounded region, right? It's cut off in this projection, and you couldn't ever really draw it. But its area is finite. Its area is actually 1 square unit total. So if you shaded it with ink, you wouldn't have enough ink to trace the outer edge. I love that blend of the finite and the infinite in the same thing in 2 different ways. Sierpinski's triangle. Start with a triangle. Legend of Zelda fans know this one. But cut out the middle fourth. Then cut out the middle fourths of all of those. Then cut out the middle fourths of all of those. And then cut out the middle fourths of all of those. And ad infinitum. Just let that keep going. It can be proven that if you continue that going, then you've removed 100% of the area of the original triangle, but there's still infinitely many points. There's still infinitely many points left that you didn't remove.
Is it accountably infinite many points or uncountably infinite many points?
I don't know. Countable. It's countable. Well, I don't know. I don't know. It's at least countable, which isn't saying anything. The Banach-Tarski paradox. There's a great video about this from Vsauce on YouTube. Take one solid sphere with volume 1 in 3D space. Break it apart into pieces, finitely many pieces that don't have any common parts. Break it apart. You can reassemble it with mathematical functions so that now you have two solid spheres, each with volume 1. So you start with something with total volume 1 and make something with total volume 2 without introducing any new stuff.
It's just really crazy.
Just confirm that is finitely many, not infinitely many?
Finitely many pieces. The thing is, the pieces are necessarily mathematically exotic. The pieces are exotic, but there's only finitely many of them. And this is introduced at the beginning of that dreadful course called measure theory, if you're a graduate math major, to show that some of your intuitive notions of how measurement works get violated. So once again, we see that you hit a contradiction and like, well, back to the drawing board, I guess that wasn't true after all.
Oh, wow.
Hilbert's Hotel. Mathematician Hilbert proposed this description of a grand hotel, and the purpose of it is to keep you from taking for granted the infinite. People are real nonchalant about infinity. And as a teacher, as a math teacher, I notice this. And I have to constantly like, no, infinity's not a number. You can't just be so nonchalant about it. Mathematician Hilbert described a hotel where for each natural number there is a room. So you have rooms starting at 1 through 14, 15 through 27, 28, 29, and it just keeps going. For every counting number, there's a room. So 7,018,010, 17,018,011, 17,018,012, and keep going. 10 sextillion, 1 quintillion, 24 quintillion, 39 trillion, 34 billion, 1,030,441. And then the next one, every counting number, there is a room. Every natural number, there is a room.
I'm pretty sure they'll have infinitely many jobs.
So, Hilbert described this to help people think about the troubles with infinity, that our instincts, our intuition, be careful. Suppose there's one guest in each room. So there's one guest for each natural number. The hotel could ask guests to change rooms, but they are not allowed to ask someone to leave, and they're not allowed to have more than one guest in a room. Okay? So 1-to-1, person to room, you can change rooms, but you can't have someone leave. Each room has one person in it, and a new guest arrives. The hotel manager is able to accommodate this extra guest. By doing what? Everyone in your room number, move over to your room number plus 1. The person in room 1 moves to room 2. Well, where does the person in room 2 go? Room 3. Where's the person in that room go? Room 4.
Imagine if you're Scott.
Where did the person in room N go? N plus 1. Everyone's able to get into a room, thus freeing up room number 1 for that additional guest. So, there, I typed out the rules for you to see. The hotel can accommodate one additional guest even if it's full. But that's not all. If infinitely many guests arrive, the hotel can still accommodate them. We're getting there.
It's an important distinction.
If you have a guest for every natural number suddenly arrives, countably infinitely many guests arrive. Every room is full. Can the hotel accommodate those? Infinitely many more? Sure.
No problem.
No problem. How? Everyone go into the room 2 times your current room number. Where does the person in room number 1 go? Room 2. How about the person in room 2? Room 4. How about the person in room 3? Room 6. And so on. The person in room N goes to room 2N. All the odd-numbered rooms are empty. All the odd-numbered rooms are empty, and each of the infinitely many guests files into the infinitely many odd-numbered rooms. And that's not all. If countably infinitely many carriages arrive, each full of countably infinitely many new guests, the hotel can accommodate them as well. The argument I actually have on a future slide, it has to do with the fact that the rational numbers are also countable. So infinity is weird, is the point. And the first person to analyze all this, it wasn't Hilbert. Hilbert came up with this illustration, but it was George Cantor, who is acknowledged as like the founder of set theory and of cardinality and of deals with infinity. Each of these sets is countably infinite. You can count it off just like you can count out the natural numbers. The natural numbers, 1, 2, 3, 4, 5, 6, 7, and so on. The even numbers, the odd numbers, the integers. Each of these have the same size of infinity. Even though, well, wait a minute. For the natural numbers, half of those are even. Half of those are odd, right? But there's still the same amount of even numbers as there are natural numbers. And Cantor showed it with things like this, that you can have a one-to-one listable mapping between the sets. If you're interested, here it is. For the even numbers can be ticked off just like the natural numbers, the odd numbers, and even the integers. If you alternate signs, you can just list them out. And what's perhaps more surprising is that the rational numbers, that's a fraction like 2 out of 3, 15 out of 18, are also countable, and Cantor introduced the diagonalization process. And this is how you would show that infinitely many carriages, each with infinitely many guests, could fill in Hilbert's Hotel, because you can just list off them, if you're systematic about it, with these diagonal markings. There's a definite listable pattern. When I teach this stuff, I use the word listable for countable sometimes. You can tick it off one, the second thing, the third thing, the fourth thing, and not skip any. But what's weird is that there's a bigger infinity than that. What's weird is that there's more than one infinity. For example, suppose you have the set of all sequences, infinitely long sequences of just zeros and ones. And suppose it's countable. Suppose I can just list it off, the first, second, third, and fourth thing, and so on. Then I can show that I haven't gotten them all. By go down the diagonal. That first one's, if that's a 0, make it a 1. If it's a 1, make it a 0. And then work diagonal down. And the second one, look at the second entry, toggle it. The third one, the third entry, toggle whatever it is. The fourth thing, the fourth entry, toggle whatever it is. And continue that process. And you can make a sequence of zeros and ones that does not belong to the original set. Because it's for sure different than each one by at least one slot. So it's a new one that wasn't in that set. But that set was infinite, right? And we came up with one not in it? That logical consequence of this was that, wow, there's a bigger infinity than the one with the natural numbers. There are levels of infinity, and they have fancy names like Aleph Naught for countably infinite, and then the continuum, the real numbers, the rational numbers, complex numbers, etc. The continuum, the set of real numbers, if you think about how you can write them using just your regular natural numbers, has the same cardinality, the same size as the power set of the natural numbers, and so sometimes it's denoted like that. Non-math people, that's like, oh, okay. In other words, exponentially bigger infinity than the usual infinity. Sometimes I call it Cantor's depths, this idea of, well, we cycle around for all the counting numbers, but what if we want to go past that? And so infinity and like infinity plus 1 and infinity plus 2, but not just like ordinals, like ranking sizes, and go around and then square that and go around and keep going. Rankings of levels of infinity, infinitely many levels of infinity. Suddenly, the doctrine of the Trinity seems like obvious. So the next level of infinity after the one we're used to with the counting numbers is labeled Aleph 1. There's its gobbledygook definition. I mention it because there was a big question. Well, we've got counting numbers like we're used to, and we have the continuum, the number line of real numbers like we're used to. Is there an infinity between those infinities? Is there an infinity between those infinities? It was number one when the mathematician Hilbert listed 23 problems in Paris in 1900. It was the number one question. Is there a size, an infinite size between the counting numbers and the real number line? Here's Hilbert himself. Died in the middle of World War II. Wow.
Did he die in the war?
I don't know.
He was so old. He wasn't a soldier, that's for
No,
sure.
no. So the continuum hypothesis stands as a candidate maybe for another axiom or a theorem to prove. The continuum hypothesis says there's not another infinity in between. You got the counting numbers and then you have the uncountable infinity of the real numbers, says the continuum hypothesis. It's not a theorem, it's a hypothesis. And there's an equivalent thing for math people, that there's not an infinity between those. And it was shown that if you assume it's true, it does not contradict the Zermelo-Frankel axioms plus the axiom of choice, C for choice. And it was shown that you can't prove it either within that axiom framework. So suddenly you have this floating, independent logical hypothesis that you can neither prove nor disprove with your axiom set. Well, dang. Something logically independent? Is that a resolution of the question? Does that answer the question? Why did I go through all that? Math is full of paradoxes. Infinity is fun. But think about with the things religions, especially Christianity, ask us to believe. An infinite God, who's everywhere and yet local at one point. Suddenly all that seems natural. Suddenly all that seems, well, how could it be any less complicated? I mean, in a world that has this stuff. It happens in science as well. I just have one example. I'm no scientist. I was a math guy, right? But the resonance structures for nitrate was mentioned in like Nabil Qureshi's book as like a major a breakthrough. Like, wow, at any moment in time, like it's simultaneously these three different shapes, these three different structures. It, for him, for Qureshi, was able to help him resolve the issue of the Trinity. Well, if in science we see this one thing being three things existing in three ways at the same time, if that happens in science, what's my grounds for objecting to it in religion? If mathematicians have these levels of infinity and infinitely many things fitting into infinitely many rooms and all that, then where's my objection to the Trinity? Like, oh, it's complicated? This was quoted on Sunday from my pastors. I also see paradoxes in myself. I also see paradoxes in me. It's what works. It's the key that fixed the lot. If something is true, then it's true along with math. If something is true, then it's true along with all the paradoxes within myself. Here's how C.S. Lewis put it. I can't give a talk without quoting C.S. Lewis. In first chapter of Problem of Pain, if any message from the core of reality ever were to reach us, we should expect to find in it just that unexpectedness, that willful, dramatic anfractuosity which we find in the Christian faith. With infinitely many infinities, with substances existing in three different states at the same time. I like this quote from Chesterton. Science and math, I would say, is getting more and more supernatural with the rapidity of a railway train written in the early 1900s. Like, there's no stopping it. Like, once Cantor broke the barrier through infinitely many infinities, once there's the axiom of choice floating around, well, the fifth and last lesson and in a way the most important. This is the one that is specific to Christianity. The others, I feel, are best resolved or melded with Christianity and all its paradoxes and infinity and finite at the same time. But this one is specific to Christianity. Important quote from a machine learning textbook that accidentally wound up in my library. As it so happens, 2 dimensions, 3 dimensions, 4 dimensions, 5 dimensions, infinitely many dimensions, uncountably infinitely many dimensions, comes up in math, comes up in applied math. It's not just a theoretical thing. And our intuition can fail badly. Projections are a way of understanding in lower dimensions things in higher dimensions. Projections are a way of describing in lower dimensions things in higher dimensions. They show up everywhere. My thesis involved a lot of C-star algebras, which are like a generalization of a generalization of a generalization of vector spaces. But to explain those ideas, they were very often explained with something, for a mathematician, very mundane, 2x2 matrices. Like these exotic, crazy things, but to understand them, we explain them in lower dimensions. Here's the problem with Christianity especially. Describing supernatural things with natural things. The kingdom of heaven, God's throne, Jesus sitting at the right hand of God, Jesus going up into heaven, Jesus coming down from heaven. All the same old elements which make up our natural life, up and down, left and right side, physical space. Important question here. If we've really received a revelation, if it's true, then can't do anything better than like crowns and thrones and music, eating and drinking, communion. Can't do better than that. Song of Solomon. To avoid a straw man argument, like I'm the straw man, like why is it that so many Christian things are described in such mundane, almost like, I think unfairly called medieval ways, like that? Well, it's the issue of projections. It's the issue of trying to describe higher dimensional things in lower dimensions. C.S. Lewis describes projections as transpositions and defines them this way, adapting something from a richer to a poorer medium. And the issue is explaining spiritual things on the natural plane. That's the issue. How do I explain spiritual truths, spiritual things with natural things? But it's not only Christianity that's doing that. We also experience it within ourselves of our emotions explained by our sensations. Think of how often, like nervousness, I'm shaky, or my heart or something, to explain the way I'm feeling, using that. And, well, it's also in statistics, trying to explain things about the population in terms of just a sample. And it happens in science, trying to explain the unseen with things that are seen. And there's one place where we see both sides of it. Try explaining something in 3 dimensions in just 2 dimensions. C.S. Lewis argues, basically sounding like a mathematician, you want to explain something in higher dimensions, sometimes you just got to explain it in lower dimensions. And that doesn't mean the higher dimensions don't exist. That just means that's our ability to communicate and explain it. And C.S. Lewis says, look to this analogy where we are able to understand both sides to appreciate the difficulty. From 3 dimensions to 2 dimensions, I doodled this little clip art to illustrate a simple projection. In 3D, the idea of a cube. In 2D, well, it would be a square, like just flat. Now imagine someone lived in 2 dimensions, and you were going to try and explain to him 3 dimensions. someone's inhabiting 2 dimensions. Suppose you're able to talk to him. You're able to descend down to his level and talk to him. How would you explain 3 dimensions to a 2-dimensional thing? Cubes, balls, the sun, the earth.
Presumably,
I'm sorry, I was working counterclockwise.
using the math.
That's what I was thinking too, actually.
Like we have R3, why don't we, you have R2, and now imagine R3. And we have R3, now
I'm
imagine
thinking of
R4.
Star Wars all of a sudden. I know you mean the 2-dimensional real numbers, right?
R2D2.
Oh, well, all you're doing is just slapping on a third, you're just saying a third thing of what I already have 2 of. You're just borrowing from 2 dimensions.
I mean, we could explain something along the lines of, well, presumably if it exists in 2D, its sensations will only be in 1D, right? Similarly to how we exist in 3D, but we only see things, see a 2D projection of like light hitting our eyes or heat across the skin or something along those lines, right? So there we have an example of them having a perception that is limited dimensionally. So the explanation could be something like, you can see things in 1D, which would probably just look like a straight line, even though you know you can walk around it or slide around or whatever, and know that it is 2D. I can see things in 2D all at once, therefore I exist in a higher 3rd dimension.
So you're taking the analogy to say, okay, I would explain it in terms of 2D to 1D.
Yeah.
Interesting. Well, you're just borrowing something I observe in my own 2D space. You're just borrowing elements, this idea of like, oh, a straight line and I can walk across it, and you use a 2-dimensional thing to prove to me that there's 3D. The Flatlander might say.
Yeah.
Like, wait a minute, but you're just describing a 2-dimensional process. A line is 1D and I can walk across it. Well, you're just borrowing from my world.
I guess you would have to prove that you can sense things in 2D all at once, which would be difficult.
And there's that proof thing.
You could technically
So I would take a cube, hold it in the plane, and rotate it so that he can get a sense of what a 3-dimensional
You transformed a square into an octagon into a
what a
heptagon.
3-dimensional rotation looks like in 2D.
He's in
Because-
2D though.
Because like you
Show him the
see,
sequence.
like when you see like, you see a lot of.
Don't forget to tell him be not afraid.
Because we see like, these computer models of say, tesseract rotations, us 3D people trying to visualize the rotation of a thing in 4D.
Trying to visualize it, but nonetheless, it's flat, and it's just like a cartoon happening in 2D. You say, well, this is representing rotation, but you're using a morphing in 2 dimension. You're borrowing elements from my world again. You say it's rotating. I see a 2-dimensional thing.
That's just morphing.
Yeah.
Not really rotating.
The sun, spheres you're just describing them as circles. Cubes are like squares. Rotations are just 2-dimensional transformations.
I'm not rotating it in 2 dimensions. I'm rotating it like this.
But the Flatlander's in 2 dimensions.
just gonna see a
So
shape
you're-
just
That
morph.
therein is the rub. Here's how C.S. Lewis put it. You keep on telling me of this other world and its unimaginable shapes, which you call solid and can rotate and stuff. But isn't it very suspicious that all the shapes which you offer me as images or reflections of the solid ones turn out on inspection to be simply the old 2-dimensional shapes of my own world as I have always known it, including on a 2D screen, simulating rotation, it is still a 2D thing. I'm not objecting, the Flatlander's objecting.
Does anything in this world rotate like that?
Is it not obvious that your vaunted other world, so far from being the archetype, is a dream which borrows all its elements from this one? All your attempts to explain it, you're just borrowing elements from mine. For any Chronicles of Narnia fans, C.S. Lewis incorporates this in The Silver Chair, when the characters are under the spell of the of the sorceress. It incorporates the same idea. To explain the sun, you use a light bulb or a candle as an analogy, like, well, you're just borrowing that element. You say there's something, but you just saw it in this world. There's not really a sun. Pascal put it this way, how dangerous it is to use the natural world to try and explain the supernatural, just like it's dangerous to try to explain to a two-dimensional person 3 dimensions. Try and explain to unbelievers the truths of Christianity or just of God using nature, the moon, the planets, creation. Well, that's going to give them ground for thinking our proofs are very weak. You're just using natural things to try and explain supernatural things, just like with 2 dimensions to explain 3 dimensions. And what does it do? Contempt. What else would it do other than arise their contempt? But here's the thing. Trying to explain the higher dimensions from the lower, that's a lot of mathematics. Here's a quote from this book. The hardest class I ever took, the geometry of manifolds. It was so hard that it was just a bewildering, like, what just happened? But at the beginning, this quote, over the past few centuries, mathematicians have developed a wondrous collection of conceptual machines designed to enable us to appear ever more deeply into the invisible world of geometry in higher dimensions. And there's a few examples, including R3. Or this here. Look at that sentence I bolded. That's from a math book. Peer ever more deeply into an invisible world is what advanced geometry is about. To try and understand complex, higher dimensional things. And how do we understand them? Well, figure out ways to think about them in terms of lower dimensions. As far as tying the not breaking the wall between Christianity and math, for me, this sentence summarizes it up. Christianity and mathematics are both giving us tools for peering deeply, more and more deeply into an invisible world. Any questions?
Okay, no, you go.
Your hand first.
Yeah, let me ignore that slide again about the axiom of choice, why it seemed so obviously false. One of them was obviously true, the other was obviously false. Is that the axiom of choice or that?
Yeah. I'm not going to be able to explain it more deeply than I did, but the axiom of choice and the well-ordering principle are logically equivalent. The well-ordering principle says that, but for any set that you can arrange it so that any subchunk has the smallest thing seems obviously false when you think about sets that just go on both ways, like a smallest negative number, a smallest dot in the plane, like that's just silly talk. And yet it's logically equivalent to saying you can make arbitrarily meaning arbitrary choices. It doesn't say what the order relation is. It's not constructive.
Or even like something like an open set of an open interval.
It doesn't specify how to do it. It just says you can do it.
So each of these infinite sets has a smallest element? You know,
Any set of elements,
Okay.
there is some way to order it, arrange it, so that when you take any subchunk, there is a smallest thing in it, says the well-ordering principle. Not necessarily the usual less than or equal. I use that as just the example symbol.
But even an infinite
But even an
subset,
infinite set, even a set that goes on forever.
that is the counterintuitive aspect, yeah.
Even an infinite set, even one that just goes on forever. you can arrange it so that it doesn't. Well, that's obviously false, but yet it's logically equivalent to something people were willing to accept.
So it's not really the axiom of choice is not controversial anymore?
That's subsiding, yes, and
Maybe a few lone
as
wolves
of maybe like
objecting,
2008,
but- Okay,
there's a quote, and I've learned this since the last time I gave this talk, as of about 2008, mathematicians that don't accept the axiom of choice are just kind of being, well, to use that word, willful again, like just trying to make a point or something, but, I mean, it's still mentioned if you use the choice axiom, it is mentioned. Like, it's good manners to say, oh, the proof uses the axiom of choice.
I have a question, it's more about like the science thing, about the nitrate existing in 3 forms.
Oh, well, any chemistry majors?
I'm going into solid state physics, maybe that's close enough.
I'm just wondering, to me that looks like it's the same shape rotated in 3 different ways. Although I guess the one on the left doesn't have a, does the one on the left have a double bond, or is it all single bonds?
Yes,
It's
it's
double
yes,
bond.
it's
It's a double
double
bond, yeah.
They are rotation.
It's just a rotation.
But are you saying they exist simultaneously as all of those?
it's like, is it a quantum
They
superposition,
share
probably?
stability.
You would know better than me.
They share
If you take those out as well,
equivalently for stability. They're all 3 happening at once. It's
Is it at
Kind
the
of hard
quantum
to
level or
explain.
not?
I assume
there-
it's a quantum thing.
I would
I would think
imagine
so.
that the 3 states, that the 3 bonding states are actually degenerate eigenstates
Okay.
occupying the same energy level.
I know exactly what that
Yeah.
is.
I don't.
So basically, if there are two, if there are two quantum states that occupy the same energy level, then any superposition of those 2 states will also occupy the same energy level. So, and can exist simultaneously without introducing time dependence into the system.
Time dependence. I love that phrase, like, I have a question. Why did I say this last lesson was uniquely Christian? What about projections and understanding the higher dimensions and the lower is unique to Christianity compared to the other religions?
You know, one of my favorite, well, perhaps probably my favorite,
Say 25:6, I see.
I guess, analogies for the incarnation is that of a circle that is also a straight line, because in a sphere, as well as on some exotic occurrences such as black holes, a straight line
We infer the unseen from the seen.
and a circle can be the same thing, even though we ordinarily do not regard the two as the same thing.
Well, you have to remove one point from the circle, and then they're topologically equivalent. See, I used a word.
For non-Euclidean geometry, though, I
Non-Euclidean.
think is what he's referring to, like going,
Oh, I don't
just
know
going in
about
a straight
non-Euclidean.
line around a
Around a
sphere.
The warping of space-time.
Okay,
is-
then-
Yeah.
Okay, but one thing that is really unique about Christianity is the way in which an infinite God is intimately involved in his finite creation. So you have the way the infinite God interacts with the finite creations is sort of and the way God reveals himself to us in that way is really unique to Christianity. Like Alex just said, the incarnation.
The
is one of those-
incarnation.
One of the most obvious ways that
Mhm.
that this is true, but you don't really have God stepping into creation in the same way in other religions. It's either like it's just
Yeah.
the divine is just like this realm that's beyond. It's kind of just inaccessible to human experience. And a lot of
God,
other
and
religions.
Christianity claims that God literally projected himself into lower dimensions so that we could experience him on
Yeah.
our dimensional level, Christianity claims. And my understanding of mathematical projection suddenly makes that seem like that's like the logical thing he would have to do. To understand higher dimensions, it has to be that the higher dimensional thing comes down to the lower. You can't get from the other. The lower dimensional is the derivative of the higher. It couldn't be the other way. We couldn't reach up and find him. He would have to project himself down here.
Question, which book of Chesterton should I start with?
Orthodoxy.
Orthodox, okay.
It's my favorite book I've ever read, even more than Mere Christianity, which is saying a lot.
Wow.
I have Mere Christianity here to flip through if you want. And Mere Mathematics. Here's Mere Mathematics.
I also like his distributive works a lot.
Here's this Encyclopedia of Mathematics. So much pre-internet days, right?
So, okay, so mathematics, as we have seen, has a lot of like kind of properties that like seem to transcend like just purely natural stuff.
Okay.
And also like, you know, I guess to the point where there have been instances in history where people have literally worshipped mathematics as if it were God.
That's true.
That's
It's
true.
like Pythagoras.
Pythagoras
Yeah.
being the most famous example.
And the Greeks preferring geometry to algebra because of like the irrational numbers.
And
Golden ratio. Good point. Good point.
We probably are about out of time here, so maybe we should thank
Yeah.
our speaker, Dr.
Yeah.
Whalen. Great job.
Thank you, everyone. You made it through the math.
We survived.
Very, very different from most reasonable things.
I can promise the rest of the meetings, the rest of the year will not be this much.
Yeah.
Yeah.
will not be this
But I
much.
did love this
No,
personally,
no,
but.
math oriented.
We
This for
we could have a rerun of James's talk.
Oh yeah, the how. See, yeah, that's another way to. do
That is
that,
an
how
awesome one as
applicable it
well.
is for explaining the world.
Yeah, I feel like there's like two different dimensions of math and apologetics, and I really loved your talk.
Oh,
It was cool. A lot
thank
of
you,
stuff.
thank you.
Just to let everyone know, we're going to be going to Whataburger after this for anyone who wants to join us for dinner. So,
Alright.
if-
Carpools will be available if needed.
yes, rides will be available, and it is the Whataburger. Okay, I think we got confused on this last time. It's the
Some people
Whataburger on Coit
The one on
and
point.
Maple Shade, I think, and it's slightly past Maple Shade.
So you have to go north.
The
So not the
Yeah,
coin.
it's-
North on Coit.
yeah, north on Coit.
North on Point.
North on Coit.
Not the one. Yes, it'll be right next to a Steak and Shake. If you are not next to a Steak and Shake, you're in the wrong place.
My phone's not drinking that, so hopefully I can put it in.
The road that's on the
Hey, how are you?